Good morning, good afternoon, good evening. My name is Tatiana Shalkivska, and I'm with the World Bank Global Facility for Disaster Reduction and Recovery, GFDRR, HydroMed team. It's a pleasure to welcome you to the fourth webinar of the Global Weather Enterprise Forum, entitled The Future Promise from the Global Weather Information. Having said that, let me introduce Vladimir Tsurkunov, lead specialist, head of the GFDRR HydroMed program, who will make an overview of the event. Over to you, Vladimir.
Good morning, good afternoon, good evening, colleagues. Our regular new participants of the Global Weather Enterprise Forum event. Yes, Anya said I'm Vladimir Tsurkunov, and now I can see on the screen many familiar names which participated in our previous events. Actually, a month ago in March, many of you participated in the second GWE online forum, and you could hear from the public and private sector experts how to increase the socio-economic benefits of weather and climate services through collaboration and partnership. As usual, the recording of that and other interesting events you can find on the Global Weather Enterprise site, www.gweforum.org. Today, as Tatiana already mentioned, we're happy to see you at the fourth event of the GWE Forum webinar. During previous GWE webinars, we had an opportunity to listen representatives from academia, Professor Tim Palmer from Oxford University, from public sector, Professor Gerhard Adrian, who is the president of WMO and GWD, German Weather Service, and from private sector, Mr. Peter Platzer, CEO of Spire Global. Today, in a few minutes, we will have a pleasure to hear from Dr. Florence Rabier, Director General of the European Center for Medium Range Weather Forecasts, ECMWF, who will present her views on the future of global weather information. Before passing the floor to Florence, let me say a few words explaining why GFDRR, Global Facility for Disaster Reduction and Recovery, where I work, and the World Bank, where GFDRR is sitting, are happy to be partners of the Global Weather Enterprise Forum and support its development. Let me start with the big picture. Some of you may know that the World Bank Group made mitigation and adaptation to climate change one of its main corporate priorities, which contributes to reaching World Bank Twin Development Goals of reaching poverty and reaching shared prosperity. The World Bank is already the largest multilateral provider of climate finance for developing countries and has increased financing to record levels over the past 2 years. The World Bank's new Climate Change Action Plan, presented earlier this April, made a commitment to increase its climate finance. On average, over the next 5 years, 35% of World Bank Group fund financing will have climate co-benefits. And more importantly to this, to our event, 50% of World Bank climate financing will support adaptation and resilience. On a more practical level, I can tell you based on my experience that more than 15 years ago, the World Bank recognized that strengthening NMHS's National Meteorological Services, and more recently improving HydroMed service delivery through public-private academic sector engagement, should become an important part of World Bank's support of developing countries. During the last 10 years, the World Bank HydroMed portfolio tripled and reached $1 billion, spreading over more than 70 projects in multiple countries. At the same time, many of my colleagues directly involved in designing and implementation of HydroMed investments know how challenging is this process, particularly in reaching sustainable results of our projects. I'm not going to describe these complexities, as probably it will require a separate webinar. But what is clear is that building partnerships between public, private sector, and academia sector is critically important for reaching success. It is also important to make our traditional partnerships with WMO and multilateral development banks more actionable. In this sense, we are proud to be co-founders and actively participate in the Alliance for HydroMed Development and Systematic Observation Financing Facility, SOF. ECMWF role in this process is, in our view, very important too. Better access of developing countries to high-quality global forecast help them and institutions like the World Bank better structure their investments and improve hydrogen and early warning service delivery. We already have positive examples of cooperation with ECMWF in multiple countries, and looking forward for scaling up this practice, contributing to sustaining benefits delivered to our clients. Finally, it would be important to know that today, April 22nd, is the Earth Day, and that there is also an opening of the Global Leaders Summit dedicated to climate change. While it is a pure coincidence that our event was organized on this particular day, it is in a way symbolic that our discussion will take place today and hopefully will contribute in a small bit to addressing the main challenges of our time. Thanks for your time. And now, before passing the floor to Florence, let me briefly introduce her to those few in the audience who does not know exactly who she is. Dr. Florence Rabier is the Director General of European Center for Medium-Range Weather Forecasts. Her career has taken her back and forth between Météo France and ECMWF. Dr. Rabier is an internationally recognized expert in numerical weather prediction, whose leadership has greatly contributed to delivering major operational changes at both ECMWF and Météo France. She is especially well known for her key role in implementing an innovative data simulation method for DVAR in 1997, which was a first worldwide, and contributed to an optimal use of satellite observations in weather forecasting. She also led an international experiment involving a measure field campaign over Antarctica in the context of the International Polar Year and WMO Thorpex program. With this, Florence, the floor is yours.
Okay, thank you very much. So, as you said, it's very exciting to meet today on this World Day, Earth Day. This is a very important, interesting day for all of us. And as you know, the Earth is burning, and ECMWF, as part of the Copernicus Climate Change Service, has today published its European State of the Climate. So obviously the WMO has published also the global state of the climate, but we published the European one, and this year, 2020, I mean, when we go back to 2020, this was really the warmest on record over Europe, 1.6 degrees more than pre-industrial areas. So this really puts in perspective how important weather and climate is, and this monitoring. So if you can display the slides, please. Thank you, Tatiana. Next slide, please. Yeah, just to introduce first ECMWF, if some of you don't know us. So we are an intergovernmental organization supported by 34 states, mainly located in Europe. But of course, we, even if we're European by nature, our collaboration is global. Of course, we have a collaboration, scientific collaboration with many countries and continents, in particular in the US, but also Brazil, Africa, China, Japan, etc. And we also deliver our products worldwide. Next slide, please. What we deliver is global weather prediction. So we are doing global numerical weather prediction. We have a model which is called the IFS, for Integrated Forecasting System. Sometimes in other parts of the world it's called the Euro. And this model is creating forecasts of the weather from days ahead to months to a season ahead. But at all these time scales, what we are running is actually not one model, but an ensemble system with an ensemble of forecasts then depicting the different scenarios of what the weather will be like in the next few days and weeks. So really, there is the primacy of this ensemble method at ECMWF. Next slide, please. Which is why when we look at the performance of our model, and we, of course, look at it through every season, every week, every day, but also in the longer term perspective, we are looking in particular at the performance of our medium range ensemble, which is then the key product of our center. This is, for instance, one example of one of our leading scores, the ones that really measure the quality of our forecast. It's about the time in the forecast in which the forecast quality falls below a certain threshold, as measured here in this continuous rank probability skill score. So you have here the long-term perspective from 1988 to now, to 2021. And the red line shows smooth line, but the blue one is actually showing the annual cycle with a better performance from time to time between winter and summer. But as you can see through the red line, there has been constant, steady improvement of the forecast model from these early stages of ECMWF, which started in 1975. But you know, this is 1998, which is quite a long time ago. So more than 20 years of improvement are shown here. So for instance, the same quality of the forecast, which was reached after 5.5 days, is now reached after 9.5 days. So actually quite a large improvement in this ensemble forecasting system in the last few decades. And so we are proud to say that we are delivering then world-leading performance global modeling. Next slide, please. So what about the future? Well, we've just published a new strategy at the beginning of the year, beginning of 2021, which covers the next 10 years until 2030. So what are the big science and technology goals for ECMWF? We are committing to produce a seamless ensemble Earth system, maximizing the use of current and upcoming observations, because everything is of course starting with observations and also finishing with observations. With the, when I say the performance of the model, of course we measure that with observations as well. So this Earth system will also be running through consistent and accurate modeling with as much as possible realistic water, energy, and carbon cycle. So carbon cycle is a new element of the strategy. We want to use advanced high-performance computing, big data and AI methodology, machine learning, to create a digital twin of the Earth with a breakthrough in realism. So this is really the highlights of our strategy as far as science and technological goals are concerned. And I will present a few examples now of what it means. Next slide, please. So moving forward then. So this is a schematic of our Earth system model. So all our forecasts from the medium range to the seasonal forecast are coupled, which means it's coupled between the atmosphere, the land, the ocean, the sea ice. We also want to include more interactivity with atmospheric composition, aerosols, ozone. So this is what is written by this further enhanced NWP, Copernicus synergies and convergence, because Copernicus is where we are doing atmospheric modeling, atmospheric composition modeling. It's very important to reduce the model bias for predictions at all time scales. And this, of course, means working a lot on the physical parameterizations and the good modeling of the numerics of the model as well. We will add complexity to our Earth system model if it improves meteorological predictions. So we are not just going to add complexity for having a fancy system. It's really every time we judge the cost benefit of adding some components in this Earth system. Very importantly, as I said, observations are the heart of it, and we want to use consistent data simulation approaches across the different Earth system components. At the moment, we have slightly different methods for the different components of the Earth system, as I say, mainly atmosphere, land and ocean. We want to get a bit more homogeneous system in the future. We will also concentrate very much in the next few years to get an optimal coupling in data simulation across the different Earth system components to better use the observation of the interface at the interface, together with an improved interface modeling, because this is very important for near surface weather prediction. Next slide, please. So towards a digital twin, I've used this word before, and we are in particular thinking of, are in the stages of becoming a partner of a new European initiative called Destination Earth, or Destiny in short, which will provide a step change for Earth system modeling and data simulation by providing technological developments to go towards high resolution and an Earth system modeling that then will be almost indistinguishable from reality. This is some illustrations of what it could look like. You have 3 globes there, which correspond to snapshots of simulations. On the left, we have the simulation at 1.4 kilometer resolution, which is what we intend to run in sort of research mode in this Destiny program. And then you have the 9 kilometer model in the middle, which is the one we are running in operation at the highest resolution. On the right-hand side, you have the 9 kilometer without deep convection to test what is the impact of parametrization. Because of course, it's not everything is about resolution. Resolution will provide a step change in accuracy, but it's also very much about tuning the physics, the data simulation that go with it. And in particular, of course, deep convection is absolutely crucial for large scales when you would run at 10 kilometers. But then, of course, it becomes a bit different. And when we go to 1 kilometer, we will not need deep convection being parameterized. It will be explicit in the equations. Next slide, please. And if you can run the animation, please. So this is now through a partnership with NVIDIA, with their Omniverse platform. This is now a little movie giving you a sort of travel, a sort of voyage through this 1.4 kilometer resolution run, which we produced on the Summit computer. This was a simulation of Hurricane Dorian in August 2019 on this Summit supercomputer. As you can see, a lot of details, a lot of fine scale structures, and it's very interesting that, of course, this comes from a global model that will be providing this sort of resolution and accuracy throughout the globe. Next slide, please. So another important component of our new strategy is about machine learning. So machine learning applications, we believe, are going to be very important in numerical weather prediction throughout the entire numerical weather prediction workflow. So the workflow is represented here from observations in the left to data simulation, forecast, post-processing, and dissemination on the right. So in all these different components of NWP, we believe that machine learning, AI, can have a role in enhancing what we are doing it more efficiently, doing it maybe with a higher level of accuracy, more cleverly. And it really starts from the selecting of observations to speeding up the model, for instance, or introducing more complicated parameterization because we can afford it through AI, through post-processing and how we use the results of our model. In the next slide, I have an example, please. So this is an example for post-processing where we think that in particular AI machine learning could be useful. This is a new tool which we have developed, Tim Hewson in particular. It's called ECPoint, and it's used to post-process rainfall predictions. This is to respond to a need to maybe do fine-scale analysis of future predictions, in particular for intense rain, in areas that might be not covered by fine-scale modeling. Because, of course, we provide the global model, at 9 kilometers at the moment. It will go to finer resolutions in the future. And in most parts of the world, people are running in their normal Met service, for instance, some limited area models. But this is not available everywhere. And so it can be very useful to actually sort of downscale what we are doing at the global scale to finer scales thanks to advanced tools, not necessarily thanks to limited area models. So this innovative post-processing uses forecast data as input. This is our forecast data. And then we train with respect to observations, and we improve the local predictions by accounting for instance, weather-dependent biases and also subgrid scale variability. This is just an example of a flood in Crete in February 2019. The observations are displayed at the bottom there, and you can see that on the western part of Crete, you have quite a large area where you had more than 75 millimeters of rain in 24 hours. So then how were we able to predict that in our Ensemble forecast? The other panels show you the probability of having more than 50 millimeters of rain over 12 hours, so quite very intense rain. You have these for forecasts at day 4, so 4 days ahead, 3 days ahead, 2 days ahead, and then 1 day ahead. On the top row, you have the products coming from the raw ensemble. So 4 days ahead, we hardly see any probability of having really high intense rainfall. Then it starts increasing a bit, and it's only on the last day really that you see a bit more probabilities of intense rainfall here on Western Crete. On the other hand, when you do the post-processing of our rainfall using this EC point, you can see how from the medium range, and I haven't shown before, but it's true also before, you can see an increase in the prediction of this intense rainfall, a steady increase with a much better capture of what is actually happening. So this is just one example. There are plenty of other applications, but this is just one example of how we intend to use machine learning. Next slide, please. So this was just then for our strategy, our technical and technological scientific developments, which are planned for the next few years to set the scene. Now, let's talk about what happens to the data. Data, of course, is the data in coming from all observations, and data out, big data coming from our NWP systems. Next slide, please. Starting with the observations. So as I said, we're running an Earth system model, which means we need observations not only of the atmosphere, but also of all the other components. The backbone of observations in meteorology are, of course, provided by in situ observation, SYNOP, but also radio sondes, etc. As you can see, it's on the left-hand side. These are the SYNOP. They are quite, of course, they are over the continents and a few over the ocean, and the geographical distribution is not very homogeneous. But on the ocean, on the right-hand side, this is the distribution of observations of salinity. Maybe it is a bit more homogeneous, but it's the number is, staggeringly low. So we would need more, of course, of these observations of all the components, and as much as possible distributed geographically in a more homogeneous manner. Next slide, please. So now going to more regional view of these distribution of observations. This is looking at the Arctic now. As you know, there had been quite a focus on the polar regions, and we've looked a lot at the influence of observations in the Arctic in particular. On the left-hand side, you have the distribution of in situ surface pressure observations, and on the right-hand side, the distribution of satellite observations. So what's striking is that few conventional data of north of 70 north. On the other hand, much more satellite observations, because of course these are the polar orbiting satellites which are displayed here. AMSUA is one of their instruments. And of course they are polar orbiting satellites, so they come very often over the poles. What is interesting to note as well on these two panels, on the left-hand side, you have the summer situation, and on the right-hand side, the winter situation. So even for conventional observations, you have a difference between season. As you can see in summer, you have more observations, in particular going to in the oceans there through the ships. On the other hand, over satellite, you would think, well, it's the same coverage really, year in, year out. But because we don't use the observation optimally over snow and sea ice, actually, it happens that in winter as well, we have less use of these observations because we can't use them properly. So this also shows that it's not just a question of distribution of data, it's really a question of well using the observations, and this really needs a lot of developments in data simulation methods and really always making progress to use as best as we can the observations at our disposal. Next slide, please. So for the time being, I've talked about number of observations. Now, what's the impact of observations? It's not completely, linear that a certain percentage of observation will give the same percentage of improvement in the model, because it depends on the quality of the forecast as well, the redundancy, etc. So this is what we try to show here. This is more now the influence on the forecast quality by different types of observations. So globally, satellite observations are dominant. They are more than 95% of the observations we actually use. On the other hand, although they are dominant in forecast quality as well, surface observations or in situ observations are also extremely important. When you look at the left-hand side, which is the normal situation, pre-COVID-19 situation, then the surface observation, in situ observations, account for more than a quarter of the forecast quality. And this is not even counting their indirect effect of helping for the calibration of satellite data and helping for the validation of the forecast, etc. This is just running a forecast and then looking at the quality of a set of forecasts. So you have satellite radiancies making for the most of the impact on the forecast, satellite winds, and then satellite radio occultation also have an impact. Now, during COVID-19, there has been a loss of in situ observation. In particular, there has been a dramatic loss of aircraft observation because, of course, there has been less aircraft movements, and some of them measure, of course, weather parameters. So this is why the surface, the influence of in situ observations has decreased. But also you can see that the satellite of radio occultations has changed. It has increased quite a lot. And this is because we have had more in 2020 of these radio occultation satellite data. If you go to the next slide, please. So on the right-hand side, this is again showing the forecast sensitivity to observation impact. So this is again showing the percentage of improvement in a forecast brought by different types of observations. So you have them all there, the microwave, temperature, water vapor, you have all sorts of satellites and in situ, etc. But the orange line there shows the difference between January 2020 to May 2020 in the impact of radio occultation data, satellite radio occultation data. So it used to provide only 5% of the quality of the data. Then in March, we implemented COSMIC 2 data. So COSMIC 2 is, after COSMIC, is another constellation of these radio occultation satellites providing huge benefit, more data, benefit to the forecast. Then on top of that, in May, we started assimilating a data from Spire. Spire is a private company with whom we had a very good collaboration in this period. Spire actually stepped up during the COVID pandemic crisis to provide data free of charge to numerical centers. They provided data free of charge to us in March, April, and we started to assimilate them quickly in May. And as you can see, every time we have an increase in the number of these radio occultation data, we have an increase in the quality, which is very beneficial. So now we go up to 15% impact from this radio occultation data. Could we have predicted that? Actually, we did sort of through simulations that we had performed a few years, before of this in 2013. So we are using advanced data simulation tools, Ensemble of data simulation in particular, to see what would be the impact of an increased number of observations measuring different parameters of the atmosphere. And we could see that there was a steady increase in the forecast quality by the decrease of this curve when we increased the number of radio occultation profiles by 1,000 there. So in a way, we had already anticipated that the impact of this data would not saturate easily, and they would still be very beneficial up to a few tens of thousands. And this is an important role of ECMWF and other NWP centers, that actually we can measure the impact of these observations in general. This was, for instance, for GPS RO, but we can do it for others. So then this can be used to actually document where we should go for the global observing system design. Next slide, please. So I talked about a good example of collaboration with the private sector with SPIRE during the pandemic in the previous slide. Now, this is something quite exciting as well coming up this year, a collaboration with a sail drone company. This is quite exciting and very innovative. These sail drones are a sort of an alternative to ship or buoys, or anyway, they are measuring the ocean in this very funky sort of windsurfing board style platform. It's very exciting because it's uncrewed, so you don't need people to operate these. It's steerable, and then it's powered by renewable energy, wind and solar energy. It's quite robust and can really withstand some really harsh environments. It has been operating in the southern oceans in particular in quite tough conditions. And it carries a lot of very interesting instruments relevant for Earth system modeling about the ocean and about the atmosphere as well. Next slide, please. So these sail drones can be used for many purposes, and the sail drone has a collaboration with many institutes, NOAA in particular. But I'm talking here about one particular use. Sail drone has been chosen to have some funding from Google Org Impact Challenge on Climate for an operational support to a new campaign that will take place this year. And they will provide in particular 6 sail drones for a year in a location that will be determined by us. And you can see there in these transects, these corridors, where we intend to be sailing these sail drones, doing the transects there over the Gulf Stream. Why the Gulf Stream? Because this is a region that is not very much simulated by our models. This is, of course, there's a lot of eddies. You need really fine resolution to describe this, but errors over this area of the Gulf Stream can have large consequences for what develops further downstream over the ocean and over Europe. This is a very intense active area of the world. So we will be looking closely. The data will be provided free of charge to everyone. So we have this collaboration with Sail Drone, but the data will be available to everyone. We will be keen to collaborate with many other institutes who want to evaluate the impact of these data. And we will look closely at air-sea fluxes, of course. This is not, we are not meteorologists, we're not the only ones interested in that. There's a collaboration as well with climate scientists looking at air-sea fluxes of carbon, which is also, of course, of interest to us. Next slide, please. So this was all the data in. So I showed the variety of data and the large opportunities we can have now. Now, what about data coming out of our systems? Once we've processed all this data, we've ingested them, we've we've done the modeling, we've produced tons of data. Then what's interesting is to provide these data, of course, to the largest possible number of users. ECMWF is moving cautiously but steadily towards open data. We have, since last year, provided free and open charts and also archive data. So archive data are quite interesting because in particular, you can go back through the whole history. You can build, of course, statistics, climatology, and they can be very useful in particular to use in the use of new AI machine learning applications. Charts, when you look at the access to our website, of course, charts are the ones that attract the most people. And this is really the fact that everybody can access our charts is very important because then we can reach everywhere in the world, even people who don't have a lot of means to have a lot of computer power, etc. Looking through a website to all these charts can actually be one benefit. So it's provided free of charge, and redistribution and commercial use is allowed with our license. Next slide, please. But it's not just about increasing the reach through making the data more available because cheaper, in particular if they are free. It's also providing a huge amount of data, and this is a real challenge for the future. So it is in our convention that we provide output to our member states in the most appropriate form. But it seems that in the future, cloud technology will possibly be the only realistic way forward, rather than shipping a huge amount of data through FTP, for instance. So it's also interesting to integrate different types of data, not just our data, but it's interesting for people to have access to our data, to satellite observations through EUMETSAT, for instance, to weather forecasts from our member states, or weather observations, also data through Copernicus services. So it's really interesting in the future to think about coordinating and collaborating in the delivering of this data. On the graph here shows the projected growth of daily real-time data produced just by ECMWF alone for our medium range forecast. So as you can see, an exponential growth. Next slide, please. So talking about cloud solutions, we are doing a pilot study now with EUMETSAT in partnership with EUMETSAT, which is called the European Weather Cloud. And of course, the intention is to bring the computation resources closer to our big data, which will be then meteorological, real-time archive and satellite data. It will be a federated cloud infrastructure, which will be available for the European meteorological infrastructure. Our council and EUMETSAT Council have also approved the use by national meteorological and hydrological services of WMO for official duty. And this fits nicely in other cloud initiatives, which in particular are in Copernicus, where we are running together with EUMETSAT and Mercator Océan Wikio, which is one of the Copernicus data information access platform. We also, at Copernicus Climate Change Service, running the Climate Data Store that offers a lot of tools close to the data, so you can manipulate the data. These are completely free data, all of them. And also we will have an atmosphere data store providing atmosphere composition data. And there will be above that, there will be Destination Earth, which will also be an initiative that will try to also build on these different initiatives to really improve access to a wealth of data from instruments, from satellites, but also from numerical modeling. Next slide, please. So now, why are we doing all that? Of course, you all know it. It's because there are so many areas benefiting from Earth system modeling. This is a slide that Steve English has put together showing all these different applications. I will not go into the details, but show a few applications, in particular in the context of Copernicus. In the next slide. So as I said, at ECMWF, we are running a numerical weather prediction, but we're also operating 2 Copernicus services. Copernicus is an EU initiative. It's a big program with several services, and it's called Europe's Eyes on Earth. And in particular here, what we were looking at from satellite is atmospheric pollution, in particular in the context of COVID-19. Through the Atmosphere Copernicus service, we have been producing some maps, animations of all the situations in Europe in particular, and looked at the situation of pollution before and after COVID and how they evolved. In the next slide, please. But actually, it's a bit more complicated than just having these eyes on Earth and looking at satellite data. Because satellite data tell you something, but the interpretation of pollution, it's not just due to sometimes the stopping of emissions. You know, the concentration of pollutants is not necessarily only due to a cut in emissions, for instance, because they are also very much conditioned by the weather situation. If you look here on the bottom plots, you have a naive interpretation of the change in pollution. This is for NO2 before and after COVID. So this is comparing the same period between 2020 and 2019. First between February and mid-March, and then mid-March to end of April for the second panel. When you just look at the bottom panel, you think, oh wow, the restrictions beginning of February or March, you know, really influenced a lot the pollution, in particular here over Europe, and actually a bit more than actually in the later period in March, April. But this is because the situation was actually quite anomalous in March. And when you actually do some weather adjusted interpretation of these maps, which are the top maps, the situation in February, March was much more bland, which means there was not so much change in the pollution due to the impact of the COVID-19. There were some reductions in pollution, but this was due to anomalous weather conditions. So then what actually you can see there, and this is using AI in this study to reconstruct this weather adjusted interpretation, what you can see is really the reduction in pollution was due to the restrictions in emissions due to COVID-19, and they were only significant in the period 15th of March and 30th of April. Next slide, please. And this can be justified by bottom up. So instead of starting by looking from the sky and then interpreting with the weather, this is instead comparing the emissions in 2019 and 2020, and then simulating with limited area models what it would mean for pollution. And then you can see that indeed this leads to a reduction in NO2 and particulate matters in this area. So all this is quite complementary then, satellite observations and other observations, and then the interpretation of the weather and numerical modeling. Next slide, please. And of course, many applications for the economy in terms of using, in particular, our climate change service data, and in particular for making the most of renewable energy, which is of course something which is very close to our hearts in the community. We've been partnering with Vortex, which is a private company in Spain, delivering products and services on wind information, in particular for setting up wind farms and operating them at best. And there are some, accurate wind forecast and analysis really matters if you want to make the most of this sort of renewable energy. So you have here some estimates that Vortex has done, that the enhanced accuracy of our reanalysis, ERA5, has produced a 3-4% error reduction compared to other reanalysis products, helping then saving money when thinking of where we're going to operate wind farms in particular. Next slide, please. Of course, we also support agriculture with climate information, and this climate data store toolbox provides some tools to plan whether some crops will be better adapted in the future in certain areas. So you can run different scenarios and see what various parameters would be in certain areas, and whether these would be a good range of parameters for, in particular, growing some different types of crops. Next slide, please. In terms of health, there was an interesting study being performed about the extent to which some vector-borne disease, such as dengue and chikungunya, could be spread over Europe, in particular, in that case, by the tiger mosquito, suddenly finding that this is actually a much more favorable environment for them to live in compared to before, because, as you know, there are of course some relation between the temperature and different weather conditions for a different sort of animals, and in particular for the tiger mosquito. So the maps on the right hand side there showed what is the prevalence of this tiger mosquito in the current period, and then what it could be if we continue to release greenhouse gases as we do in the future, in the next 100 years. And then you can see that there's much more prevalence in Europe of this tiger mosquito, and then more risk of having this disease spreading as well. Next slide, please. So at conclusion, where are we going to take cooperation, taking it to the next level? So I've tried throughout this presentation, actually, I've tried to highlight some of the cooperation we had. Of course, ECMWF is a member and cooperating state organization, so the obvious, we are born from collaboration, and of course these are our obvious partners in terms of collaboration. We also have formal cooperation agreement with agencies, satellite agency, EUMETSAT, ESA. We also have a very strong collaboration with NOAA, with CMA. We collaborate through research projects and WMO. So this is sort of our, if you want, our standard partners, our historical partners. In the next slide, please. And I believe, of course, they will continue to be our most prevalent partners. But WMO really plays a key role in enhancing the collaboration through all of us and through various applications. This is an example of the very good seasonal, sub-seasonal to seasonal project, for which we are providing data with other centers that are available through this WMO project. And there was, in particular, this study recently highlighted in the news by the University of Leeds and others in partnership with Africa, with ACMAD, to predict the location of meningitis outbreak, where they could be based on weather condition in the next few weeks. So that's also important. I've talked about a bit about the climate threat to dengue, for instance, but this is really the more short-term spread of diseases through favorable, unfortunately, weather conditions sometimes. Next slide, please. Now I would like to talk about the SOF, the Systematic Observation Financing Facility. I think this is very important to support. This is an excellent initiative to support the expansion of observations, in situ observations, because, as I've said before, they are not spread evenly throughout the globe, and they are very important, in particular in areas where there are not so many of them. On the left-hand side, you can see the distribution of SYNOP data, and color-coded, you have some in the islands, Pacific Islands, in the US, Europe, and Australia. And on the right-hand side, we have the influence on these forecasts taken all together on forecast quality. This is the influence per observations, but when you average over all of them. And it's the same color code. So let's say that over the globe, these SYNOPs have a 6% influence per data, 0.06. Then over continental USA or over Europe, actually they have a bit less influence because there are so many of them. But if you go to Australia, they already have more influence than in these regions. And if you go to the Pacific Islands, they have even more influence. So this is an illustration that not all observations are equal, even if they are of the same quality. Actually having more observations in areas which are not so well documented at the moment is very, very important. And this is what SOF is supporting. And we are happy to support, as well as other centers, having a role in quantifying the impact of observations which can help to see where it would be more beneficial to add some observations. Next slide, please. And to finish, I would like to talk about other collaborations with this time more technology partners. And in particular, of course, we are running our model on HPC, on high performance computing, and we've been making use of some of the largest supercomputers in the world. And we are very happy about the partnership. And in particular, we had won this grant to be able to run on this summit. You can see here Niels Veddy in front of the supercomputer summit in Oak Ridge, who was very happy to have been granted access, and that's where we could run our 1.4 kilometer model. We had also been running on PISENT in Switzerland. Of course, our next generation model, Atos, will also be larger than what we have now. We're expecting to be running on Euro HPC machine and also the Riken machine Fugaku in Japan. This is very interesting to be running experiments on these very large machines because it tells you where the bottlenecks are at the moment in our system, and then we can see what sort of progress we can make to run more operationally on our own supercomputer in the future. Next slide, please. We're also collaborating with private companies for computing activities. So Atos will be delivering our next supercomputer, and we have created this Center of Excellence, which is called Center of Excellence in HPC, AI, and Quantum Computing for Weather and Climate. It's with Atos, supported by other companies, AMD, Mellanox, NVIDIA, and DDN. Our first two projects are on machine learning and the development of a CPU, GPU-based version of our model, the IFS. We also had a very exciting project with Maxar, and I would like to thank in particular Brian Etherton. We had a contract to run the IFS model on Amazon Web Services cloud computing resources. And so this company, Maxar, took our model and adapted it to run on Amazon Web Services, and together then we can test feasibility, scalability, and performance. So this is a new area possibly for us, this partnership with private company on the technology field, but quite a useful one to progress in the future. Next slide, please. So this is my concluding slide. So look to the future, very exciting, many things happen, exciting scientific developments, enhanced use of observations. I'm not talking about as well all the new observations that will be coming. This is extremely exciting with all the new observations, in particular from EUMETSAT and NOAA, etc. It's really exciting to have new satellites, but it's also, we have to continue to work on making better use of them. Going to finer scales in an ensemble Earth system model, more realism in physical representation and water, energy and carbon cycle. We have these challenges to move to a digital twin of the Earth, with major technological development, introducing AI machine learning throughout numerical weather prediction workflow. We have opportunities to have more observations from satellite, private companies, and Internet of Things. We will enhance our distribution through cloud infrastructure. We will move to open data. Beyond the weather, there's also atmospheric composition, floods, fire, climate are progressing very fast and providing huge benefits to society. And as I said at the end, we think we will build on enhanced partnerships with our historical partners, of course, but also co-design with industry will play a key role in the future. And with this, I will stop. Over to you.
Well, Thank you, Florence. It was very rich, both in details and in strategic thinking for the future for ECMWF and for the whole business, I guess, because you touched upon many important things. With this, I'm inviting colleagues who actually we have, during all your presentation, we had over 180 participants, and we got 3 questions so far from the chat. So I'm inviting other colleagues to consider, based on this presentation, what are the burning questions from your side. Let me start with a question which is closer to to our role, development institution, which came from Alan. Are you optimistic that the data gaps, such as in some developing countries of in situ observations, can be filled in future? Rainfall predictions in tropical Africa are relatively poor, so obtaining more data for such initializing forecasts, but also for verification, is important. Any prospects for the future?
Well, I've talked about this this SOF initiative, and I'm putting big hopes in this initiative because it's a very well-structured initiative, and I think it really learns from the lessons from the past and how some projects have been helping these developing countries and taking it to another dimension to have the global picture, and also supporting these countries, not only just deploying observations, but continuing to run them. And I think it's interesting to show the benefit of this SOF initiative. So observations, of course, have an impact locally, but they have an impact globally. So it's very interesting to take both into account, and motivating countries to deploy these observations, supported, of course, by finances and by donors. I think it's extremely important. It's extremely important for everybody, primarily for these countries, but it will also have a huge importance globally. And what is important as well, I didn't mention it, but of course it's very, very important, is the sharing of observations, because of course we should also try to share more of the observations that are already available. And sometimes we also need to help some of the countries providing observations. Well, maybe they have observations, but it's delivering them, which is also complicated. So this is also one step where I think we should really focus the effort to help doing observations and sharing observations for the good of everybody.
Well, I can disagree with you on that, because we're also supporting SOF. There are a number of questions which are coming. Let me start with the first one, which arrived earlier, and that was from Jean-Pierre Way, if I pronounce his name correctly. Does ECMWF intends to make freely available IFCs real-time data through APIs?
So we are progressing towards making IFS real-time data available. So we are freely available. We are working on, we of course have standard data being available, you know, the standard data provided by WMO, but we are planning to maybe make more available. They will be made available in a simpler way to start with, but hopefully we will also make them available through APIs as well in the future. We go step by step, as I said. We started with the maps, with the archive, and then we are working on making more data available. There will be some proposals coming to Council this year, so we'll see where we take it. But I'm quite optimistic that in the next year we will have some more data being available in real time as well.
Thanks. Let me now ask a question from Bob Goldhammer, International Association of Energy Managers. His question is, the slides about the improvements in forecasting ability were of course very informative, but what I found to be of even greater importance were the slides about predicting the impacts of the weather on people. The one about the spread of dengue fever due to changing climate conditions is a great example of its as it relates to impacts of the weather. The ability to better and more accurately forecast the short-term and long-term impacts of weather is key to those of us in energy management. I think it's more like a statement, but it's difficult to disagree. Indeed, it illustrates the importance of what your forecasts do for significant policy making decisions, which our politicians should make at this point of time. Let me also there are a couple of three actually questions which is difficult to judge which one is more important. But let me start with a comment on the sail drones, which came from Cooper van Ranken. Those sail drones look expensive to operate. There are thousands of fishing vessels which focus effort right on the Gulf Stream and shelf break. Many have surface MET and SST sensors units already on board. Could be a nice collaborative approach for more sustainable observations in this tricky yet crucial region. Any comments on that?
No, it's true. We take whatever whatever is available, and having these observation of opportunity of putting more observations in the vessels that are flying that are going through the oceans. Of course, it's very important, and adding observations to any platform would be of use indeed. The interest of the sail drone is that maybe they are able to go to where maybe boats and ships are not willing to go. In particular, if they can be robust under hurricane, conditions, that would be great, and that would be much better to send a sail drone rather than to send, of course, some crewed ships there.
Okay, there is a scientific question. I don't know the meaning of it, but you, of course, may comment. And that came from Christoph Ramshorn. The question is, can you comment on the impact of soundings on forecast quality?
Yeah, the impact of soundings, of course, it is very large. I didn't show that, but of course, radio sondes have a large impact on forecast quality. It's even more striking that the forecast quality improves even more when you put a radio sonde in less observed area. But so it's even more striking, the difference between well observed and not so well observed area. And maybe I would like to reiterate a comment. Really, radio sondes are the backbone of everything for doing calibration of satellites as well. These are really important data because they are covering the whole atmosphere and many parameters. So I think it's difficult to underestimate we should not underestimate the impact of in situ observations, and in particular radio sondes. And it's not only the impact we measure as directly if we remove them for the forecast or not, it's also all this indirect impact of calibration of other instruments and validation of our forecast that make a huge difference.
Okay, thank you. Questions keep coming. So let me pass the one from Bruce Ford. And the question was, after the COVID-19 pandemic, subsidies and aviation recovers and returns to growth. Do you believe the aircraft-based observations will return to the pre-COVID position, the FOSI studies?
So they will grow again. They will come back to where they were, sort of. Now, of course, this proportion, it's a sort of pie chart. So it depends, because if we have more of other data, it's a relative importance. So of course they are important, but if we have suddenly many more, in particular satellite observations with MTG, we will have huge number of observations, very good observations with others as well. So it all depends what the proportion of observations and what the others do as well. So I'm pretty sure that the aircraft, it will again, start growing, the number of aircraft, the importance will grow again. But it might not reach the same level, because in the meantime, we might have had other observations being introduced in the system, and the sum of the influence is 100%, so it can't go beyond that.
Thanks. There was earlier question from Dominique Marbotti. What was the impact of using ADM EOLIS data?
very good impact. Good question, Dominique, and it has indeed been having one of the best impact. In particular, when you see how few observations there are. So we have been quite struck by the influence of ADM Aulus, and this is it corroborates the impression we had that really we are missing wind observations, and satellite provide a lot of temperature, humidity observations, but not so much wind, and we knew that wind observations would be absolutely important. So we are really very positive about ADM Aulus and the influence that these observations have on the forecast. So we would really welcome having more of these instruments if possible in the future, because really it held its promise.
Okay, there are two questions for somebody which name is AJ. I don't know whether it's, what does that mean? But the first question is, will the commercial sail drone observations be shareable with other national net centers, the existing data sharing agreements between the agencies?
I believe they will be put on the GTS, so they will be shared indeed normally as without even having data sharing agreements, at least the ones that have been that are going to be provided through this Google or Climate Challenge. The data will be free to use for everybody, so they will be shared. We'll make sure they are shared. Yeah.
And the second question from the same participant is, NOAA recently signed a data sharing agreement with Ørsted Wind Energy to share data for research that will in turn help climate change observation and study, as well as help Ørsted operate.
Okay. Well, we also share our data for research applications, and we would also welcome any data that wind energy companies have that would help validate our model, for instance. So it's always good to share and to you might have some observations, we might have some forecast data. So indeed, this sort of collaboration is very useful.
Two other questions from Karam Essequini. First one, does the recommendation of unified data sharing policy that was approved by WMO Infrastructure Commission a big milestones towards more accuracy in NWP product? I assume it's not clear what is written, but it's probably the case.
Yeah. Well, sure. Any progress in data sharing is going to be absolutely great for NWP accuracy, and we really welcome the developments that are being planned at WMO. Yeah.
Another question from Leonard Smith to you. While the sum of impact of observations is always 100%, could it be that some observations, like those from aircraft, improve the probability forecasts of important events? How could you distinguish these from contributions to the standard general measure of the forecast?
That's a very good question, Lenny, and thank you. We should probably concentrate more on trying to respond to that question. What we are doing, we want to provide some significant results. So usually, of course, we mix together, we merge together months and months of data and experiments to have a robust signal on the impact of observations. We can also do it on a day-to-day basis, and indeed we can compute this forecast sensitivity to observation on a day-to-day basis. So then we can see which ones are more important, and we could, we can look over a cyclone developing, over a storm developing. We haven't maybe done so systematically, but sometimes we do look at the impact of various forecasts for different sorts of conditions, of weather conditions. But I expect it depends whether it's at the large scale, the small scale, at the short range and longer range. For instance, we could see, we have made some data denial experiments showing that satellite observations were absolutely essential to predict the track of storms coming over from Africa to the Caribbean there, that you wouldn't see them at all without satellite. It doesn't mean that satellites are the most important in the last day before the forecasts, when they come over some islands, you know, the surface pressure or the buoys are then the most important to track down where the cyclone is. So we haven't done anything systematic, and I wouldn't be able to tell you which sort of observations are the most important. I can tell you that surface pressure observations are really, really important, and that's why we see so much impact of SYNOP in particular. And a good balance between mass and wind, so they're all quite important, but I wouldn't be able to say which one are the most important for particular events.
Okay, it's a future developments. A question from Tahara in Japan. Would you introduce us the conditions to use the European Weather Cloud and other clouds by academic and commercial sector?
Yes, so the European Weather Cloud is still very much a pilot in development, and for the time being, it's restricted to member states and to national Met services then. But it's not yet in its full, you know, it's not yet fully developed so that we are able to share it beyond. But yes, we will definitely share the conditions on how people can use it. Mainly for the time being, it is for official duty that we say that Met services could use it.
Sorry to keep you asking questions from people, but it's coming. The question from Mashauri. Some countries in Africa are improving their observations capacities. Is there a prospect to blend these in situ data with the satellite data in the current models to improve observations, particularly in Africa?
We are doing blending in a way in data simulation. We are indeed, in our data simulation system, we are using everything that has a reasonable quality, and we are blending them between the satellite data and the in situ data. In situ data, in particular over Africa, are very, very important because using satellite data over land to initialize weather models, it's not so obvious to really represent the lower parts of the atmosphere and include that, because we have some difficulty in representing the emissivity, the skin temperature, etc. So using satellite observations down to the surface is always a bit more tricky for us. So blending in a way in situ data with satellite data by data simulation is a way to improve the analysis, the condition which appear everywhere. It's particularly useful over continental surfaces, so in particular Africa. And that would, of course, improve forecasts.
Another question from Krista Chipilski. Does ECMWF plan to assimilate more ground-based remote sensing profilers in the future, and perhaps combine their measurements with new emerging in situ observation technologies, such as weather sensing drones?
Yeah, we are progressing, you know, towards using more types of observations. I've sort of shown which are the ones we are working on at the moment. But of course, we are making progress, and we have planned to use more and more of these new sort of exotic types of observations. But this is, you know, it takes a lot of time to actually work with observations, understand their weaknesses, their biases, their errors, and then including them in the system. So we can't work with too many types of observations in, you know, at the same time. But we indeed will continue to progress in using more observations. In particular, recently we introduced some MODES data, which are new aircraft data based from radar at the airports. So this is one of the developments we did recently. We also started assimilating descent data from radiosondes. So that's also, you know, I like these new developments, but I think really we should also make the most of what we already have and try to enhance even more. I think this idea of developing a bit more the radio zones and using the descent data is just fantastic, because, you know, with the same balloon and then the same instrument, then you can also measure twice, two profiles in a way. So we are trying to keep the balance between using new observations, which require a lot of work too, and also enhancing the use of our current observations, which is also quite demanding.
Indeed. When we're looking at the operating and maintenance costs for our client countries in developing world, the first observations which are suffering because of the high cost, of course, it's up there. And that's, again, could have been considerable improvement for the quality of forecast. Anyway, it seemed that at least I don't see any particular question. There were some comments with thanks to you for this elaborate responses. We still have a few minutes if participants.
Yeah, I would like to pick up maybe one comment there, which maybe I didn't quite understand the question, so I would like to do this comment from AJ. So the point of Saildron and Orsted comment was that each national med center should try to ensure that data agreements with commercial entities should include pre-arrangement to share data with other national med centers. Absolutely right. It would be really nice if we could. That comes back to the point of, yes, please, if we can have the most exchange of data. So maybe I didn't quite understand the question before. So yes, absolutely.
Okay, there are some signs of good quality. We still have there are a lot of people showing their satisfaction, I guess. We still have 130 people online, but unless there is anybody who wants to make important statement or ask question, I think we're getting close to closure, and I suppose to say something which again it's thanks coming. There is another question from Dominique Margotti. You mentioned that carbon is an important new development in your strategy. When would you expect to be able to provide information about sources and sinks of atmospheric CO2?
Okay, yes, I did mention it, but it's true, I didn't explain very much what we were doing there. So as part of Copernicus, Climate Change Service and Atmosphere Monitoring Service, more on the atmosphere monitoring, we are used to monitoring already carbon concentrations, CO2 concentrations, but going down to the emissions it's much more complicated. Going down to the sources, the emissions of CO2, you have to understand the whole carbon cycle, which is why it is important to have a better carbon cycle in our model, because then you can go back to the emissions as well, but it needs new satellite data as well. And so in the next phase of Copernicus, starting in the middle of this year, there will be this CO2 emission monitoring and verification support initiative, and there will be satellites from ESA launched in the next few years. Before having these satellites, the new satellites that will be even better at seeing from space a bit where the emissions are, we already are going to work on enhancing our system to try to find the sources and sinks of anthropogenic CO2. We hope to have a sort of pre-operational system in 2023, but that will be before using new satellite data, but we will already have something sort of in place to be able to routinely see what we can get from these sources and sinks of anthropogenic CO2. But definitely we should be ready for the next global stocktake then in 2028. Hopefully that will be where we are fully ready with new satellites and all.
Thank you. The most recent question came from Aki Milia. Out of curiosity question, did the reduction of aircraft data reduce the forecast skill in spring 2020? And or did the increased availability of GNSS radio occultation data compensate or overcompensate for that in a statistically meaningful level?
Yes, so what we saw is that actually there was not so much difference between 2019 and 2020 in terms of forecast performance. So we believe that the GNSS RO data compensated for the aircraft loss. So we didn't see a big degradation. We didn't see a big improvement just coming from the observations. But of course, we also changed the system, gradually. So it's a bit difficult to quantify. But all in all, we don't think that there has been a big decrease because other observations picked up and so improved the forecast and compensated.
Okay, there are other messages thanking you for good responses. I guess we can stop asking people to introduce questions. I can just reiterate what people already provided in response to your question. That thank you so much for sharing ECMWF experience. To me, it shows the breadth of what you do and the huge value you deliver to the globe. Let's be, up to the to this recognition and from the angle of our institutional interest, I would hope that this great work which ECMWF and Europe in general is delivering to developing countries will have a greater role in strengthening the net service delivery for the nations in these countries, and that our cooperation with ECMWF will indeed improve this. Thank you again, and thanks everybody for participating in this. It's surprising that still well over 100 people was listening. It means it's a sign that you indeed provided the value to all people who participated. And again, the coming applauds, great job, very impressive, ambitious program, coming decade. So
thank you to you for the invitation. It was a pleasure to contribute to this webinar. So thank you very much, Vladimir, the World Bank and the Global Weather Enterprise Forum. It was a pleasure.
Thank you, and let's wait for the future good events. Thank you, everybody.
Bye-bye.
Bye-bye.